done. Okay, right. Just have a look at page 18 of your worksheet, or rather page 17 of your worksheet. Oh, okay, generally is here. Okay, hi generally, you just joined in. We actually just started the lesson. We are looking at page 17 of your worksheet. Okay, now for page 17, part C, you cannot do part A and B yet from above because it's actually on a different temperature. It's actually in a different chapter called temperature. So we don't do that one first. What we can do is actually part C. All right. So in your case, you have a block of aluminium of mass 670 grams that is heated at a constant rate of 95 watts for 6 minutes. The specific capacity of aluminium is 910 joules per kg per Kelvin. The initial temperature of the block is 24 degrees centigrade. Now, assuming that there are no thermal energy losses to the surrounding, show that the final temperature of the block is 80 degrees centigrade. Okay. So the keyword here is this one, no energy loss to the surrounding, no heat loss to the surrounding. So in a way, it could actually just mean this from what you've been reading here. Your heat supplied by heater is actually just the heat gain by the block. Okay. Now, if you have heat loss, you will have a plus H here. But since the question already said that you have no thermal energy losses to the surrounding, this one is actually not even inside your equation. What you have is this one. So whatever heat energy is supplied by your heater is actually your heat gained by your block itself. So this one, you can actually just use equation Q equals to MC delta theta. Heat supply is MC delta theta. Where in your case, Q is the heat supplied by your heater. It could be PT or VIT. Okay, because it came from this general equation in the first place. Q over T. So Q is PT, and at the same time P is VI, right? So it's VIT. Okay, so but in your case, you don't have the value for your voltage as well as your current. Instead, you have the value for your power. So you use power instead. Power multiplied with your time. Remember to change your answer to remember to change your time from minutes to second. Okay, so PT equals to MC delta T, 95 minutes, 95 watts equals to 6 minutes times 60 seconds times the mass of the block of 0.67 kg times with your specific heat capacity of 910 joules per kg. And then what is your temperature rise? What is your temperature difference? Okay, they already told you that the initial temperature is 24 degrees. So you go rise up to a certain temperature T. You're interested in finding out what's this T. So just take T minus 24. Okay. Higher value minus lower value. Okay. This one, just take the higher value minus the lower value. Okay. So eventually you get the answer as T equals to 80.1 degrees centigrade or degrees Celsius. So round it up to 2SF, it is 80 degrees shown. Okay, so so good. Okay, then I'll move on to the next page. All right. Okay, now next page, they tell you, clear off everything. Now, in practice, there are actually energy losses to the surrounding. Before this, we actually said energy losses to the surroundings can be ignored, but here they say yes, it's actually still present. They tell you that the actual variation with time T of the temperature theta of the block is shown here. Use whatever information that you have in one to draw on the figure, a line to represent the temperature of the block, assuming no energy losses to the surroundings. Okay, so just now it was said that when you had no heat loss, your temperature went from 24 degrees centigrade to 80 degrees centigrade. But right now they want this. If you now have heat loss, if you still start out with 24 degrees centigrade, what's actually supposed to be the actual temperature here? Yeah, this is what you're interested in finding out with heat losses to the surrounding. So the actual original graph that was drawn for you was this one. Oh, sorry. What was I explaining just now? This one they say draw a line to represent the temperature of the block representing no energy losses to the surrounding. It's actually referring to this. Okay. I went ahead and explained this one. This one is actually for this one. Okay. All right. This one is actually for this one. Okay, so just disregard what I just said. All right. Just now I will explain the wrong thing. I accidentally saw this as take into account heat losses to the surrounding. Here they say assume no heat losses to the surrounding. Okay, so here, what is the line that tells you the temperature of the block, assuming no heat loss to the surroundings, assuming no energy losses to the surrounding? When you had no heat loss just now in the previous page, you already calculated that it will go from a temperature of 24 degrees centigrade to 80 degrees centigrade. So you know that the endpoints are going to be 24 degrees here and 80 degrees here. Okay, and then after that, you should have a line joining those 2 points. How do you know it's going to be a linear line in the first place rather than a curve like what you were seeing below here? In your diagram, you're actually seeing this line already drawn, but it's a curve. And then now you see that you're supposed to draw a line representing no heat losses. So you only know the 2 points, but how is the variation of the line going to be? How do you know that it's going to be a straight line in the first place? Okay. Now, one easy way of looking at that would be to use the equation that you've done just now. You can see that Q is mc delta theta. If Q, m and theta are constant, Q is mc delta theta just now. And then after that, we say that PT is mc delta t. If P, M, and C is constant, T is actually proportional to your temperature change lah. All right, so it's showing you a linear relationship just by looking at this. That's the reason why I can say that the actual line should have been a straight line like this. Okay, no curves whatsoever, just a straight line. All right, so this is actually for part 1 over here. All right, now for part 2, they are telling you use back the same figure, calculate the total energy loss to the surroundings during the heating process. Okay, this one, they are already asking you to consider the fact that you have heat losses to surrounding. But here they want you to find out specifically what was the amount of heat loss. So now if you look at the original graph that was already there in your question, when you had heat loss, your temperature was actually going from 24 degrees centigrade to 64 degrees centigrade. Again, this is the actual final temperature of your block with heat loss included. Okay, so what they want is this. You went from here to here. What was the heat loss in this process? What was the heat loss in this process? So you can make use of your energy equation again. If you talk about the energy equation just now, we say heat supplied by heater is going to be equal to the heat gain by block plus heat loss to surroundings. Okay, so this is the equation in word form lah. If you write it in symbol form, it will be Q equals to mc delta theta plus H. The H is your heat loss. Then expand it a bit further. PT equals to mc delta theta plus H. So you want to find your heat loss, you just substitute the variables for whatever you know from the equation. You know what is PT? It's 95 times 360 seconds. You know what was MC delta theta. You know the mass. You know the specific capacity. You also know the temperature difference now. Your temperature difference is 64 minus 24. This one is taking into account the temperature difference when you have heat loss. Okay, so 64 minus 24, then plus with H. So your heat loss is just going to be 9.81 times 10 power 3 joules, just like that. Okay, right. Now, there's also another different way of finding the heat loss. That one is by looking at this, at the graph itself. You see, in your case, you look at the graphs that you've just drawn, the two lines. The one that you draw, this one is the one with no heat loss. Then the one at the bottom is actually with heat loss. Okay, now you look at the final part, final temperature of your block at the end. With no heat loss, it was going to give you 80 degrees centigrade. With heat loss, it's going to give you 64 degrees centigrade. Now, this one represents a temperature difference of 80 minus 64, giving you a temperature difference of 16 degrees. You could have actually just found out the heat loss directly by just using Q equals to MC theta. Okay, there's a different method of finding the same energy loss or heat loss. You just find out the temperature difference due to heat loss, which is 16 degrees. And then after that, you just use the equation MC delta theta. Sub in the values for the mass, specific heat capacity, as well as that temperature difference. This is representing the amount of heat loss that you have. Okay, so this one is just another different way of doing the same thing. Okay, so this one is done. Then after that, I move on to the last part of your notes. Then after that, we can wrap up this chapter. Okay, so if you look at your notes again, for page 6 and 7, we went through finding specific capacity for solid and liquid. There was another part we did not do yet. That one is determining specific latent heat. Specifically, what you have here is specific latent heat of vaporization. Okay, you also have experiments to determine latent heat of fusion, but it's not written inside your notes now. Okay, we just make use of vaporization first. Now, if you wanted to find out the specific latent heat of vaporization of a particular liquid, let's just say water, you can do so by conducting an experiment. Now, if you wanted to conduct an experiment, generally your experiment will look like this. Okay, what you will have to do is this. Whatever liquid whose latent heat of vaporization you want to find out, you need to heat it up by a coil carrying a steady current of I1 and a PD of V1. Okay, so the liquid that you have, you need to put it inside some sort of flask with holes in it. Okay, so that liquid must be heated by something. You have a heating element here. You are using an electrical heating element. You want to make sure that when you heat it up, you know the voltage and the current through your heater. This is so that you can actually find out the heat energy supply. Because in the previous example, we already said that power is Q over T, Q is PT, and then it can be expanded to VIT. Okay, so you want to know the current, you want to know the voltage, so that eventually you can find out how much heat energy do you actually supply to heat the liquid. All right, so now you heat up the liquid boils, okay, eventually. So when it boils, it will change into vapor, it will change into gas. The gas produced will actually pass through the holes inside the container. This is your original container. It's some sort of flask with holes in it. So once your liquid boils, it changes from liquid to gas. It will now flow out from the holes inside your flask and into your condenser. Okay, so this flask here is contained inside another larger container. Okay, when your vapor flows out, it can't flow out all the way outside. It's still contained inside another container. So as your vapor escapes from the inner container or flask through the holes, it will flow downwards through your condenser. Okay, this part here is your condenser, where you actually have cold water running in and out. Cold water comes inside here, and then cold water goes out here. So your vapor, it will pass through this condenser here, and then it will be quickly cooled down. So when it passes through the condenser, it's quickly cooled down, the vapor will actually condense back. Okay, here we say it condenses back to water lah. It actually should be, it condenses back to liquid lah. All right. Here, because this one, it condenses back to water. The moment I say this condenses back to water, this one, the liquid under test is actually water. Okay, so this, in order to make the terms more consistent, you probably be better if you just write it condenses back to liquid now. Okay, as the vapor passes through the condenser, it condenses back to liquid. All right. So now, what you want to do then is that you continue heating up your liquid until the temperature at all parts of your apparatus have steadied. All right. You only really start collecting data when the temperature throughout your apparatus is constant or steady. You don't want to start the experiment when the temperature is still fluctuating. You want to make sure that the temperature throughout is constant or steady before you start collecting data. All right. So what you want to collect from this experiment is the vapor that has condensed back to liquid. All right, you see your vapor flows down, it condenses back to liquid. You want to collect the liquid that is condensed back. All right, because the general idea is this: if you refer back to the definition of specific latent heat, it is the heat energy required to heat energy per unit mass to convert or change the phase of a substance from one to another at constant temperature, right? So for phase changes involving latent heat, we generally use this one, right? ml. So L is your specific latent heat. L can be found from heat Q over M. Okay, so if you know what was the heat energy supplied to cause the phase change, this is heat energy to cause phase change. This M is actually the mass that has changed phase. Okay, this M here is not the original mass of whatever substance that you're boiling or melting. This mass is actually supposed to be the mass that has actually changed phase. Okay, so if you're talking about for vaporization, the mass that has changed phase here should refer to the mass of liquid that has changed to vapor in the first place. Okay, so the mass of that vapor is actually the same as the mass of the liquid the mass of that vapor is actually the same as the mass that has condensed, which you are trying to collect over here. Okay, that's the reason why you would have a beaker right at the bottom of the condenser here, because you want to collect the condensed vapor so that you can measure the mass. That mass itself is actually the mass that has changed phase. All right. Now, when you want to collect the condensed vapor, generally speaking, you tend to collect it over a specific time interval. Okay, you will tend to collect it over a specific time interval, say maybe every 5 minutes. Okay, Now you collect it every 5 minutes until you notice that the mass collected per unit time is constant. Yeah, this one I think we need to change again. The mass of liquid. Okay, until the mass of liquid collected per unit time interval is constant. All right, what do I mean by that? Is easier to refer back to the table here. Here I mentioned that you collect the condensed vapor or you collect the liquid every 5 minutes. So you only continue doing so until you notice that the mass is constant, right? So what I mean is that you can actually just look at the table below here. If let's just say I try to collect the mass of the liquid that is condensed, I do it maybe 5 times. The mass of liquid collected in every 5 minutes in grams for my first trial is 23. For my second trial is 32. And then after that, for my subsequent trial, third, fourth, and fifth time, I noticed that it's all going to be at 45. This is what we mean by the mass of liquid collected per unit time interval is constant. Now, when you have mass collected per unit time being constant, this one is telling you you have achieved constant boiling rate, okay? Constant boiling rate is when the mass of liquid that you collected per unit time interval is constant, all right? So that's what we mean by that. And then your table here, this one I think you also need to change. It's not mass of water, it's actually mass of liquid, okay? The mass of liquid collected in 5 minutes per gram. If you reach 45 for the subsequent trials, this one is already constant boiling rate, okay? You really only start to consider your masses once you reach constant boiling rate, okay? Anything before that, you do not consider. It's only after you reach constant boiling rate that you consider the mass, all right? So that one is out of the way. Okay, now, there could also be some different ways in which you can see whether something has reached constant boiling rate. Other than the table here, sometimes they could probably give you a graph and you're supposed to be able to deduce when have you reached constant boiling rate. Say for example, if I told you that we plotted a graph of the total mass collected against time, this one is the graph, total mass against time. You continue collecting the mass from t equals to 0 to some value, and then you plot a graph. The graph looks like this. Okay, so at some point you will notice that the graph is actually curving. And then at one point you will notice that the graph is actually straight. Now at the point where the graph is actually straight, this is where you actually have achieved constant boiling rate. Because you can see it like this. If I were to divide your graph into equal time intervals, you will see that my mass is the same per unit time interval. If let's just say I divide this by say, instead I divide this by delta t, and delta t, you will notice that my delta m is going to be the same. Oh wait. Okay, my delta m is going to be the same. This one at the top actually doesn't count, right? Wait a moment. Oh, okay, sorry. The one at the bottom actually doesn't count. The one at the top actually does count. Let me just get this done properly. Okay, so when you have a straight line graph, this one is already telling you you have constant mass of liquid collected per unit time. per unit time interval, okay? Because you see the straight line graph essentially means that if let's just say the first T1 here I get a mass of delta M. For the same T1, delta T later on, I'm still getting the same mass of delta M. And then for the third delta T later on, I'm still getting the same mass change of delta M. Okay, you're actually getting the same mass per unit time interval, all right? So this is another way in which you can see whether something has reached constant boiling rate. Okay, now the mass is only considered once you reach constant boiling rate. So in your case, you would take the value as 45 grams here. Now from there, you will then move on to your energy equation so that you can find out your specific latent heat of vaporization. Now, if you want to talk about the energy equation here, according to conservation of energy, what we will tell you is that the electrical energy supplied by your heater is equals to the heat gained by the liquid to vaporize plus heat loss to your surroundings. So written in the proper equations, written with the proper symbols, it will be V1 I1T equals to M1 LV plus H. Okay, the M1 here being your 45 grams. Your T here, the time interval here being your 5 minutes. Okay, so just bear this in mind. Now, if you were at this stage here, last week when we talked about finding specific heat capacity from by using the same energy equation, what we did was that we go and ignore heat loss and then after that proceeded to find the specific heat capacity, right? You see this equation that is written here has some similarity to what we learned last week when it came to finding specific heat capacity. Okay, VIT equals to MC delta T plus H. So in your case that time, it was mentioned that because your apparatus is very well insulated so that your heat loss to surrounding is very little to the point that it's negligible, you can actually kind of ignore H and then after that work out to find C, right? But in your current case, when it comes to specific latent heat or vaporization, you cannot do the same thing. You cannot just simply say that, oh, heat loss to the surroundings is negligible, so I can just ignore it and then after that move on to find L. No, you cannot do that. Because in the first place, your apparatus here, like this, you see is kind of large with a beaker here, with a condenser here, and then with a large container which contains another container. If you want to insulate the entire thing, it will be very, very, very difficult. Okay, so no matter what you do to insulate this entire apparatus, there will always be some leakages somewhere where the heat can always escape. So here you cannot really insulate it as well as compared to the previous two examples. So we cannot just simply say, oh, heat loss is going to be ignored here. Okay, so we cannot ignore heat loss here. If we ignore heat loss here, when it is significant, whatever value of L that we find will be very inaccurate. So one way of actually overcoming this kind of problem is that we would actually repeat the experiment. But when we repeat the experiment, we would use a different setting for your heater. We will use a new heater current, I2, and a voltage V2. So that this time, the new mass M2 or vapor that has condensed that we collect in the same time interval is collected. All right. So you go and use a new setting for your power with different current I2, with different voltage V2. You collect the new mass of condensed vapor in the same time interval. Now, this one is very important, the part where you say you collect it back in the same time interval. If before this, you collected it in a time of 5 minutes for the first time, the second time you do the same thing with different power setting, you must collect over the same time at 5 minutes also. Okay, so this is one thing to take note of. You must collect it over the same time for the two different power settings. So once you have done that, you will notice that your energy equation is quite similar with the first one. The second time you do this, it will be V2 I2T equals to M2 LV plus H. All right. Now, what we can then do from here is that we will actually say that we can actually take equation 2 minus equation 1. Right? When you see these two equations, you can actually take equation 2 minus equation 1, where you see that the h, which we previously could not ignore, will now cancel off if we take one equation minus of the other. Now, here, the heat loss for both cases is actually going to be the same. All right. That's why we can say that if we take equation 2 minus equation 1, they will just straight away cancel each other off. The heat loss here in both cases is actually the same. All right. I'll explain why later. Now, if you take both equations and minus 1 over the other, your resulting equation will actually be V2I2 minus V1I1 times T equals to M2 minus M1 times LV, from which you can find your specific latent heat. All right. So for your case here, when you want to find specific latent heat or vaporization, you just make sure you take two different set of power settings, do the experiment twice, and then find the two different equations, and then you minus them off so that you can find out what is L. All right. Now, why is it in the first place that heat loss can be eliminated? Now, the reason why we can say heat loss can be eliminated here, even though we are using different power settings, is because of two things. We can say that heat loss is the same, number one, because you have same time of exposure. All right. Remember, I still mentioned to you just now, if for the first time you did the experiment, you use 5 minutes when collecting the mass. The second time you use a different power setting, the mass that you collect must be also be for 5 minutes. Okay. So here, because of that, I can say that the exposure time for my apparatus is actually the same. Time taken T is the same for both cases. Now, how does heat loss get affected by exposure time? It will be better to look at some examples like this. If let's just say, for example, I give you exposure time. I gave you two different beakers. They are all placed in the same room. Okay, wait. Maybe not. Yeah, same room. I can think of it as same room. They both contain liquid. This one is liquid at 100 degrees centigrade. This one is also liquid at 100 degrees centigrade. Now, the room temperature, say for example, here is 20 degrees centigrade for both. Okay. I tell you that this one is beaker A, and then this one is beaker B. All right. Now, beaker A, I leave it alone for say 5 minutes. But beaker B, I leave it alone for 30 minutes. Now, in my current case here, regardless of whether it was beaker A or B, I would definitely have heat loss to the surroundings because, as I mentioned to you last week, heat energy tends to flow from higher temperature to lower temperature. So in your case, you actually have heat loss. Let's just say that you have HA here, and then this one here, you have HB here. So if I ask you to compare between these two right now, both of them are the same. The only difference is the exposure time, the time that you leave them alone. So between beaker A and between beaker B, which one will actually have a higher amount of heat loss? You will probably be saying that the heat loss for beaker B is more than beaker A, right? Because more time for heat to be lost or dissipated. Okay. So this is the effect of exposure time. All right. You can have two different situations where everything else is the same. The only difference is the time that you leave it alone, the exposure time. The one with the larger exposure time would actually cause a higher heat loss. Okay, so this one you can actually kind of say this exposure time larger, heat loss is larger. All right, so this is effect of exposure time. Now, what is the effect of temperature difference then? The second factor here that affects heat loss is actually temperature difference. Okay, here I could say that my heat loss for both cases under the different power settings are the same because we also have same temperature difference. Now, what we mean by that is this. If I talk to you about, say, temperature difference, I give you again two different beakers. This one is beaker C, and this one is, say, beaker D. Okay, this one, let me just draw it here. Again, they are filled with liquid. This one is same 100 degrees centigrade, filled with liquid 100 degrees centigrade. This one, as I mentioned, is beaker C. This one, as I mentioned, is beaker D. Okay, now in my case, I leave both of them in the same, I leave both of them alone for the same time. Maybe this one I tell you is 20 minutes. This one also is 20 minutes. Okay. So the only thing that's different here now is that the room in which I place these two beakers. If the room that I place these two beakers is different, the temperature is different. Say maybe in one room, the temperature was, say, 20 degrees centigrade. And then another one, maybe I put inside a freezer where the temperature is, say, negative 30 degrees centigrade. Okay, just as an example. Okay, so in my case, both of these beakers would, both of these beakers containing liquid will have heat loss, but the amount of heat that is lost will not be the same. Okay, so this one you will have heat loss C, this one you will have heat loss D. Okay, now if you look at this one, okay, maybe I make this a more extreme case so that it's easier to see. Maybe say, for example, this one I put it in some sort of hot room or boiler room. This one is 60 degrees. Okay, so that the example is much clearer. Now you look at 100 degrees and 60 degrees. Your temperature difference is actually just 40 degrees. But if you look at for beaker D, you have 100 degrees and negative 30 degrees. Your temperature difference is actually 130 degrees. Okay, so now if I ask you which one will actually experience a larger amount of heat loss, it will actually be beaker D. Okay, heat loss of beaker D would be more than heat loss of beaker C. Okay, because the temperature difference for D is larger. Okay, so in general, what we can say here is if your temperature difference is larger, your heat loss would be larger. Okay, so that's why D here would have a larger heat loss. Now, if you relate back to what was written inside the notes, your heat loss can be said to be the same for both the different power settings just now, because number one, you have same exposure time. The time taken T for both cases was the same at 5 minutes. All right. And then after that, number two, in the first place, you also had same temperature difference. Now, when you started to boil the liquid, let's just say it's water right now, the boiling temperature is 100 degrees. And then you actually conducted the experiment inside the same room, the room temperature should actually be the same. the difference between the boiling temperature and room temperature remains unchanged, thus the temperature difference is the same for both cases. So because of these two reasons, you can actually say that heat loss is going to be the same. All right, no difference. That's why you can actually take one equation minus of the other, they will cancel off. So in your current case, when you do this, the specific latent heat of vaporization that you find is actually accurate. It's not like the specific heat capacity that you found in the last lesson. That one we said that the moment you ignore H, your answer was going to be an overestimate. It's not really that accurate as you would like it. But this one, for latent heat, is actually accurate because your heat loss was properly taken into account and eliminated. All right. Now, some of you may be asking, what is the effect of having different power settings? Now, if you have different power setting, it really just affects the time taken to reach constant boiling rate and the amount of water collected per unit time. If you're using a higher power setting, it just means that your liquid will boil faster, you will actually reach constant boiling rate faster, and at the same time, because you have more power, more heating, the mass collected per unit time is also going to be larger. Yeah, this one I think you can also just change it. Liquid, okay? Liquid collected per unit time. All right. In my case, because here I think somehow when I was doing the notes, I keep thinking the liquid is water. That's why I unconsciously just write water. But if you want it to be properly termed, you can just write liquid. All right. The higher the power, the faster you reach constant boiling rate and the more liquid collected per unit time. All right. Okay. So with this, we are done with the concept teaching part for thermal properties. All right. Okay. If you just look at page 3 of your worksheet, all right. This one is talking about finding specific latent heat, but this one different from your notes is finding latent heat of fusion. Okay, when you try to melt ice into water from solid to liquid, in other words. Okay, so this is November 5th. Sorry, what year is this? This one is June 15 P41. Let's have a look at that. So June 15 P41. Question 3. They ask you to define specific latent heat. Okay, so for your case, specific latent heat, you can actually just take the definition from your note. It is just simply referring to the heat energy per unit mass required to cause a phase change at constant temperature. All right. So heat energy required to cause phase change is 1 mark. At constant temperature, this is another mark. Okay, you must always have the term constant temperature there. Otherwise, you won't get the full marks. All right. So this one is okay. And you see, in your current case here, this one is just a general definition of specific latent heat. They didn't say whether it's vaporization or whether it's fusion. So you don't really need to say what kind of phase change was it, whether was it from solid to liquid or liquid to gas. You can just say it's just phase change. All right. Now, look at part B. In part B, we mentioned that an electrical heater is immersed in some melting ice that is contained inside a funnel as shown in the figure. The heater is switched on, and when the ice is melting at a constant rate, the mass M of ice melted in 5 minutes is noted together with the power of the heater. The power P of the heater is then increased. A new reading for the mass M of ice melted in 5 minutes is recorded when ice is melting at a constant rate. So data for the power P and mass collected are given in the table below. Okay, now for this particular case, some things to note. They mentioned to you that the heater was switched on and ice is melting at a constant rate. Okay, so remember just now in the previous part or in the notes, I mentioned to you when you try to boil your liquid when conducting the experiment, you only really start collecting the mass after you've reached constant boiling rate. In your current case, when you're melting this ice, you're also doing something similar. You must reach constant melting rate. Okay, when the melting is at a constant rate, this is actually constant melting rate, which in turn will tell you this now. The mass of water collected per unit time or per unit time interval is the same. Okay, only then you start taking the value of the masses. All right. Then after that, you read further down the question. They also mention to you that later on, after they collect the mass in a time of 5 minutes, they purposely increase the power of the heater. And then this time they collect the new mass also for the same time. See, this one they say was taken for 5 minutes the first time. The second time is also taken for same 5 minutes. So must be same time interval. All right. So if you look at the table actually has a missing blank there. The next part of the question actually asks you to complete it. Okay, the next part in the next page, they ask you to complete the figure to determine the mass melted per second for each power of the heater. What is the amount of mass melted per second in grams? Okay, find out the mass M melted per second in grams per second. So all you just need to do is you take the value of the mass, divide by time. So at 70 watts, take the mass, divide by seconds. You're going to get 0.26. And then at 110 watts, you take the mass, divide by time again, which is 5 minutes times 60 seconds. You're going to get the answer at 0.38 grams per second. Okay, so this is the mass per second. All right. Then after that, they ask you, use the data from the completed figure to determine the value for specific latent heat of fusion L of ice. Okay. Then after that, you see some equations written here. All right. Now, when you want to write out your energy equations, you need to be careful a bit on whether your case that is being considered is a boiling case or a melting case. What do I mean by that is this. If necessary, you are boiling something, let's just say that you are boiling something. When you are boiling something, say water lah. This one is 100 degrees centigrade. Your room temperature is probably 27 degrees centigrade. You actually have heat loss from your water boiling to the surroundings. This one you have heat loss. Okay, so when you're trying to heat up your water so that it boils, that time it was mentioned to you that heat supplied by heater is equals to heat to vaporize liquid or boiled liquid plus heat loss to surroundings. Okay, so let me just be a bit clearer here. This one say is your heater. The heater will supply heat to your water. This one is your heat supply. Then your heat supply, it will go into heating the water, and then a portion of it will be lost as heat to surroundings. Okay, so that's why I can say this thing here. Your heat supplied by your heater, a portion of it went into vaporizing the liquid, and then a portion of it was lost to the surroundings. Okay, so this one is for boiling case. Now, when you're talking about melting for ice, this one is slightly different. So if I tell you melting, Again, I still have the same beaker, but this time I have ice. Let's say that this are all ice. Again, I have my heater. All right. Now, my ice by default would be at a temperature of 0 degrees centigrade. And then my temperature of my surroundings will be 27 degrees. Okay. So right now, when it comes to melting the ice will actually gain heat energy from the heater. It will also gain heat energy from your surroundings. Heat gain from surrounding. Okay, so in terms of the direction of heat flow from surroundings or to surrounding, it will actually be different between boiling and melting. For the case of boiling, the water itself is at a higher temperature than the surrounding, so heat energy will flow away from it. That's why you have heat loss. But in the case of ice, where the temperature is at 0 degrees, its temperature is lower than the surrounding. So heat energy flows from higher temperature to lower temperature. It will actually flow towards the ice. Wait now, guys, just give me a minute. Something came up. Sorry for the distraction. Okay, right. Yeah, back to what I was just saying just now. When you have ice is by right at 0 degrees centigrade, and then your temperature of the surroundings is 27 degrees. So as I mentioned before, heat always goes from higher temperature to lower temperature. Your ice would actually be gaining heat from the surroundings in addition to heat supplied by your heater. So when you actually want to write out the energy equation, it will actually be like this. Heat supplied by heater is equal to heat supplied by heater plus heat gain from surroundings is actually equal to the heat to melt the solid. Okay, so notice the term for heat loss or heat gain here is actually on different side of your equation. If it was, say, boiling, heat loss to surrounding on the right side. If it was melting, it is heat gain from surroundings. It will be on the left side of your equation. Okay, so just so you are clear right now a bit, all right? So it could be heat gain from surroundings, it could be heat loss to surrounding. It depends on whether you're boiling or melting in the first place, because we know that heat energy always tends to flow from higher temperature to lower temperature, all right? So in your case, because you're talking about latent heat of fusion is talking about melting, you will eventually have heat gain from surroundings, not heat loss to surroundings. So your equation by right would actually be something that looks like this. It's written down there lah. Okay, heat supplied by heater plus heat gain from surroundings is equals to heat to melt the ice. All right. So your goal now is to find out some equation based on this, right? So if you try to write it out in equation form, it will be PT plus H equals to ML. All right. And then after that, there's one thing here that you can actually do from this. You can actually modify this equation to be in terms of per unit time, where this equation you divide by time. So it becomes P plus H over T equals to M over T times L. All right. Now, the reason why I want to use, I would want to use the equation in terms of per unit time right now is because the value of mass that I'm given, which you found in the previous table, is actually already in per unit time. This value that you have here is not mass itself. It is mass per unit time. So in order to make your life a lot easier, you go and modify the equation so that it is per unit time, like what you're seeing right over here, right? So this one here is what you're seeing right over here, okay? So you try to write out the equations in terms of per unit time, have it done for the two different power settings, and then after that you take one equation minus the other, you should be able to find out what is L, the specific latency of fusion. Okay, so in your case, this one will be P1 plus H over T equals to M1 over T times L. Second one will be P2 plus H over T equals to M2 over T times L. So take equation 2 minus equation 1 or equation 1 minus equation 2, whichever it is, it doesn't matter. In my case, I took equation 2 minus equation 1. I will get this expression. So from there, you just sub in the values that you can see from the table. P1 is 110, P2 is 110, P1 is 70. The mass per unit time for 2 is 0.38. Mass per unit time for 1 is 0.26. Eventually, the answer will be 333 joules per gram. Okay, so this one should be okay. So far, so good. Right. Now, you don't really need to change your units for mass from kg, from gram to kg, because the answer here is already in grams. All right. You can actually look at the analysis of your units if you wanted to. What would be the unit of L? If you're talking about units of power, this one is already joules per second. And then the unit of your mass per unit time here is kg. It's gram per second. Eventually, you realize that the per second will cancel, giving you joule per grams for L. So there's actually no conversions required for your units during your calculation here. Okay, so no need to change anything. Now, what if you don't want to convert your equation into per unit time and do it like what I've just written here? Instead, you want to use that the original equation that you have over here. That one is also perfectly fine to do. Okay, it's perfectly fine if you want to do that because you actually have the value for time. All right. If you had just wanted to do this one for the first part here, you can. All right. Because you actually have the unit for time. All right. Because T here is actually 5 minutes. You convert to second will be 5 times 60. It will be 300 seconds. Okay. So if you have wanted to use the first equation rather than converting it to per unit time, you can. All right. Because you already have the value of the masses also in the first place for 5 minutes. And you know the time is also 5 minutes. Okay. So it just be P1T plus H equals to M1L. P2T plus H equals to M2L. So then you take equation 2 minus equation 1, it will be P2 minus P1 times T, M2 minus M1 times L. So your time you already know as 300 seconds is 5 times 60. Your mass M2 and M1, this one you would actually need to use the value of mass over here, from here. Okay, this one is already the mass melted in 5 minutes. So you use this value of mass. Instead of mass per second, you don't need to use this. You use the one in the next column. All right. So you do that one, eventually you still get back the same answer. No? L is equals to 333 joules per gram. It doesn't matter. All right. Just use which one you are most comfortable with and you'll be okay. All right. Now look at part 2. They ask you to find out the rate h of thermal energy gained by the ice from the surroundings. Okay, so just now I explained to you that your case will be heat gain from surroundings. So when you see this one, they tell you find out the heat gained by the ice from the surroundings. This one should not be a surprise. Okay, it will not be heat loss to surroundings. It is heat gain from surroundings. Okay, so when you want to find heat gain from surroundings, is actually talking about finding this H over T. All right. Now, if you want to find H over T, you can either just sub in the values inside equation 1 or sub in the values inside equation 2. Just use either one of the equations, right? With the answer that you have found here, you can actually make use of equation 1 and 2 to find out what is H over T. So in my case, I'm actually using back equation 1. P1 plus H over T equals to M1 over T times L. P1 is 70. H over T is what I want to find. The mass per unit time is 0.26 gram per second. The specific latent heat of fusion I already found is 233. So your H over T, the rate of heat energy gain from surroundings will be 16.7 watts. Okay. Yeah, another thing I should probably mention here is that the moment you see rate here, this one already tells you is per unit time. Okay, that's why I can just directly use whatever equation that I have here in the beginning. All right. If you want to use equation 2, it's also okay. You will still get back the same answer. All right. And needless to say, if you did not use your equations in terms of per unit time in the first place, instead you had used this form of your equation that is not in per unit time, you could have also still continue using it, where you just either pick equation 1 or 2 and sub in your values. So in your case here, if I use back equation 1, P1T plus H equals to M1L, you again sub in the values, the power, the time, the mass, as well as the specific latent heat. You're going to get this value of H here. But this one is the thermal energy, not in terms of time. This one is the total thermal energy gained by surroundings. But the question wants it for unit time because they call it rate, right? So all you just need to do is that you just take the same value of H divided by time. It'll be 4974 divided by 5 minutes divided by 60 seconds, giving you 16.6 watts. Okay, right? So this one should be okay. All right, then we go on to the next question. This one will be under page 5 of your worksheet. Let's have a look at page 5 of your worksheet. Okay. Okay, page 5, June 2015, P42. Okay, now this define specific latent heat. We've actually done the similar thing just now. I don't think this one we need to go through it again. It's just simply heat energy needed per unit mass to change the phase of a substance at constant temperature. That's all there is to it. All right, nothing to do anything. All right, it's just something from your notes. Okay, now look at part B. Okay, for part B, if you read this one is actually somewhat related to boiling. Okay, for part B, you have a beaker containing a liquid placed on a balance as shown in the figure. A heater of power 110 watts is immersed inside the liquid. The heater is switched on, and when the liquid is boiling, balance readings M are taken at corresponding times T. A graph of the variation with time T of the balance reading M is shown here. All right. So you are actually heating up this liquid so that it boils off. So the liquid that you have here eventually will change off to gas. Okay. So when your liquid changes to gas, one of the things that you should be able to realize is that because your liquid is changing to gas here, the mass of your liquid will actually decrease with time. So the mass of the liquid is actually being measured by your balance here, by your top band balance here. Right? So they use it to produce a graph, which is what you're seeing in the figure here. All right, this graph that you're seeing is representing to you the mass of the liquid inside the beaker. And notice that it's decreasing with time. It's decreasing with time because your liquid is being boiled off. So that's good. Okay, now then after that, you look at the next part of the question. The next part of the question is asking you this. State the feature of the graph that you see, which suggests that the liquid is boiling at steady rate. How do I know that your boiling rate is steady? How do I know that you reach constant boiling rate? So just now in the notes I mentioned, in addition to say seeing from the table, you can actually see from the graphs itself if they ever give you. All right. I mentioned to you, the moment you see that your graph is a straight line, it really means constant boiling rate, right? So here is the same thing, similar concept. Just that in your case here, your mass is decreasing. This one is because it's the mass of the liquid remaining. All right. So you see that it's a straight line. So since this is a straight line, it really means to you that you are having constant boiling rate. You can say a number of things now. Either because you see a straight line, a linear slope, or constant slope, or the best one would be just to say that because you see that the gradient is constant. Okay. So here I think I can actually show it to you quite easily. If let's say you divide this into equal time intervals, this one is delta t, this one is delta t, then this one is delta t. Your mass of water or liquid that has boiled off will be given by this. Okay, this one will be your delta m. Okay, this one will always be same with each other because your graph is a straight line. Okay, that's why here we can say you've reached constant boiling rate. All right. Okay, now look at part 2. Part 2 is saying that use your data from the same graph to determine a value for the specific latency of vaporization of the liquid. Okay, now just now you actually did some questions that relate to finding specific latent heat. Even in the notes also you went through that example. For those cases, you notice that you have to use two different equations, and then you take one equation minus off the other, right? In order to find the value of L. You can't really use it here because you see your current case, they never give you a different power setting. They never mention to you that they are repeating the experiment with a different power setting. They never did any of that. So you cannot use the method that you have used previously, where you use two different equations and one minus off the other. This one you have to just somehow ignore heat loss to surroundings. The only way you can do this question is to ignore heat loss to surroundings. Okay. So if you look at this one, I can tell you this heat supply by heater is equals to heat to boil liquid and heat loss to surroundings. Okay, this is by right supposed to be the actual energy equation. So if I try to write it out, this one will be PT ml plus H. So if you ignore heat loss, this one is not in anymore. You will actually get PT equals to ml, where L is PT divided by M. So you can actually make use of this to find out L from the graph. Okay. Now, what do I mean by this is that, do you know the value of the power in the first place? Power here is 110. And then the value of your T and your M, you can actually find from your graph. All right. So your T here is actually the time taken. Your M here is actually the mass that has changed phase. In other words, from liquid to solid. All right. So you can actually make use of this equation directly. L equals to PT over M. And then after that, you just read off some values on the graph. Let's just say, for example, I want to read this. This one is my T. Okay. T is 6 minutes. So at T 6 minutes, what is my mass that has actually boiled off? What is the mass that has actually changed phase? That one will actually be given by something like this here. Okay, this one will actually be my M, which would actually be something, some values now. Okay, I think I have to read it directly from here. This one is 20 divided by 10. So one box is 2. This one is 370. This is 372. Okay, so this one is 372. And then this one here is it right in the middle? This one here, one, two, three, four, five. This one also 6 boxes. So this one is 332. Okay. From what I can see, this one seems to be 332. You might be getting different values. Okay, it's 372 and 332. So my mass here is actually going to be 372 minus 332. So in my case, it will actually be 40 grams. Okay, so I already know my time, I already know my mass. Okay, and I also know my power, so I can find out my specific latent heat. All right, now you don't really necessarily need to follow the same timing as me. You can actually follow your own different timing. For example, you could probably also do for 4 minutes, and then after that find the corresponding mass change, which is given right over here. Okay, you're free to use whichever values you want, but I would just suggest that you always try to take at least half the line. Okay, just like what you're doing for paper 3. Okay, when you're finding gradient, remember when you're finding gradient, you always need to take over half the line. So here, if you want to take the values, I would suggest doing it over at least half the line. All right, so some of the values that you have, you should be able to get the answer for L. So it should be 110 times with 6 minutes. Change to seconds, don't forget. And then your mass must be in kg, because you see this one is joules per kg. So 40 grams divided by 1000 will be 0.04. Your answer will be 110 times 6 times 60 divided by 0.04. You're going to get 990 joules per kg. All right. Right, so you're going to get answer as 990 joules per kg, just like that. Now, there was another different way of doing this, but I think this one is a bit more tedious or complicated. This one is actually you trying to equate the equation into a straight line equation and then relating it to the graph. Because you see, I can say that PT is equals to ML, and then I rearrange this, I will get M is equals to PL over T. Your graph here is actually mass versus time, where mass is actually y-axis, time is actually x-axis. So here you try to do it in such a way that the y-axis is M mass, the x-axis is time t, you're going to get this expression, y equals to mx plus c. The gradient is actually p over l. So from there, you find the gradient of your line equated to power over L, you will be able to find out the value of L itself. Okay. But I think this one is a bit more tedious now. I mean, it's just unnecessary. This one is actually not as good as this now. This one is pretty direct. All right. Now for part 3, one last thing they ask you, state with a reason whether the value that you've just determined in 2 over here is likely to be an overestimate or an underestimate of the normally accepted value of the specific latent heat of vaporization of the liquid. So because you ignore heat loss here to calculate L, do you think it's going to be an overestimate or underestimate? So taking a hint from what we learned from determining specific heat capacity, we know that if you ignore heat loss, it often leads to an overestimation of your values. So this one you can just say, there is actually heat loss to surroundings. The value will be an overestimate. Okay. The value will be an overestimate. Heat is lost to the surroundings, so the value will be an overestimate. Okay. Right. Yeah. One thing I just noticed. Okay. For part 2, if you just excuse me for a while, for part 2, I just noticed that your answer here has a 10 power 5, but here I give you 990. The order of magnitude doesn't seem to be correct, right? So I must have forgotten something here. Wait, gram change to kg, 40 divided by 1000 is 0.04. 110 times 6 times 60 divided by this. Oh, okay, sorry. My calculation, my working is correct. It's just that my answer is not correct. I forgot to change it to the correct power 10. This one is 9.90 times 10 power 5 joules per kg. Okay. Yeah, so there's a slight mistake here just now what I mentioned. I mentioned this one is 990, right? I converted the power of 10 wrongly. It's supposed to be 9.9 times 10 power 5. Okay. Consistent with what you're seeing here. Right? Okay, so this one should be okay. Then we again move on to the next question. Let me know if you need something sorted out. No, I'll just move on. Okay, now the next question you can probably have a look at is page 19. Let's have a look at page 19. Oh, the diagram. Have a look at page 19. Let's have a look at page 19. This is November 17 P42. Okay, page 17 from just now. Again, same thing. What is meant by specific latent heat? Thermal energy per unit mass required to cause a phase change of a substance at constant temperature. Just take the definition from your notes. Okay. Part B is where things are a bit different. Now, you have a beaker of boiling water that is placed on the pan of a balance as illustrated in the figure. Water is maintained at its boiling point by means of a heater. The change M in the balance reading in 300 seconds is determined for 2 different input powers to the heater. The results are shown in the figure below here. Okay. Now, if you look at this figure is actually the same as the previous question that you just did. Both are still talking about boiling some sort of liquid off and then the liquid is actually placed on top of some sort of balance. The only difference now is that they show how the liquid was heated in the first place. And you notice now they say to you that they heat it, or they heat the liquid so that it boils, and then after that they collected the mass. They found out the change in mass. They found out the mass of water that has actually boiled off in 300 seconds under two different power settings. So here, when you read this, you see got two different power settings, and then they go and collect the mass over some given time. You know you're going to have to use the two different equations method to find out the value of L eventually. All right, but that one is for the next page now. All right, we haven't gone through that. If you look at part 1, they tell you energy is supplied continuously by the heater. Okay, energy is supplied continuously by the heater. Now, state where in this experiment is external work done. All right, where would be external work done? Where in your current diagram or system is actually work being done? It can be work done on, it can be work done by, it doesn't matter. Just as long as you identify what is actually having the work done on it or by it. Okay, so the easiest thing to see is actually the water itself. Okay, so if you see this one, originally you have your liquid. Yeah, I don't like this now. Originally you have your liquid here like this. Once you try to boil it off, you have some liquid and then some vapor. Okay, this one is liquid, this one is liquid, and then this one is gas. Okay, so where is external work done? From what you've just done in this chapter early on, I mentioned to you, whenever you want to find out whether work is done, you tend to use this equation, pressure times change in volume, or rather you just look for any volume changes for any work done, for any work to be done. Okay, so because work done is pressure times change in volume, so if you want to see whether work is done, you just look for any volume changes. So coincidentally, you can see from here, when you boil liquid into gas, you vaporize it, you can actually have changes in volume. So you have work done. Okay, so here you single out the case of the water. The statements here may be a bit different. I'll just write it another way for you. This one is for this one. When water changes to steam, its volume increases. Okay. Work is done by steam to expand against the atmosphere. Okay. Like this one is kind of similar to what we've just done before. When water changes the steam, its volume increases. So work is done by steam to expand against the atmosphere. All right. The one that the marking scheme wrote was this one, where they tell you that when water changes to steam, it pushes against the atmosphere. So work is done against the atmosphere. Okay. So this one is another different. This one is the marking scheme. All right. This one is what the marking scheme wrote. when your water change to steam is pushing against atmosphere, work is actually being done against the atmosphere. This one they single out work being done against atmosphere. But the answer that I just wrote here, I am singling out the steam. Work is done by steam. This one is work is done on atmosphere. Okay, they're actually focusing on two different things. Okay, the marking scheme is saying work is done on the atmosphere. This answer here is talking about work is done by steam. Okay, they are kind of talking about the same thing. All right, it's just a difference in the point of view. All right. Okay, then if you move on to part two is saying where in your system right now is internal energy increasing. Okay, so this one you can actually think of it in this manner. Remember in your first part of your lesson, I mentioned a few things. Changes in internal energy can be found by two different ways, from the different definition of internal energy itself or from thermodynamic first law. So this one, I can say to you, internal energy is Ke plus Pe. So change in internal energy is equals to change in Ke plus change in Pe. And then another one is from thermodynamic first law, where delta U is delta Q plus delta W. Okay, so you could have probably see changes in internal energy from these two different ways. Okay, so they want you to single out where is internal energy increasing. Is it the atmosphere? Is it the water or some other place? So the easiest thing you can actually say is this, where you say that it's actually the internal energy of water increasing, because when water changes to steam, or rather from liquid to vapor, the potential energy of molecules increases, right? It'll probably be easier to, it probably flows better if you write the second sentence first, followed by this. Okay, when water changes from liquid to vapor, the potential energy of molecules increases because bonds are being broken. Wait, let me just write this out for you properly. Okay, maybe this one I erase it. How you go and see these things? When water changes to steam, this one is more like a complete answer now. When water changes to steam, bonds are broken, thus molecular PE increase. Temperature remains constant at boiling. Thus molecular Ke is constant. Okay, so from here, if change in Ke is constant, but PE is increasing, obviously internal energy increase no, when water changes to steam. Okay, this one is more like for this one. This is how you make sense of the statement that the marking scheme has given you. Okay, they didn't tell you the full story. They just give you bits and pieces of it. When water changes to steam from liquid to vapor, the potential energy of molecule increase. Therefore, internal energy of water increase. The complete story is this one, to make sense of what they're saying. Okay, so that one is okay, supposed to be okay. Now, if you wanted to somehow talk about increases in the internal energy and explain and explain why the internal energy increase. You see, your question here asks you to explain. They didn't just only ask you to state where is the internal energy increasing. They ask you to explain why is it increasing. Now, let's just say you wanted to explain from thermodynamic first law, delta U equals to delta Q plus delta W to explain why water is having its internal energy increasing. You can also kind of explain it. Number one, you can just say heat supplied to boil water. Therefore, heat is supplied to boil water. This one indirectly already means to you delta Q is positive. Now, then when water changes to steam or gas or vapor or whatever, this one volume increases. So work is done by system. Therefore, delta W is negative. All right. Okay, now, just now I kind of mentioned that you can also explain why internal energy increase from here, right? Actually, you can't. Okay, you actually can't explain it using thermodynamic first law because you see you have two contradicting answers. When you boil water, you know that heat is supplied, so delta Q is positive. So this one I know is going to be positive. But then when you try to explain the work done part, you know in the first place water changes to steam, so volume is increasing. Work must be done by the system. Delta W is negative. So this one is negative. So because you have positive Q and negative W, this one is a bit ambiguous because you see you will need to have, if delta Q is more than delta W, therefore delta U will be positive. But if delta W is more than delta Q, therefore delta U is negative. So in my case, I can't really explain from the information given which one of this is actually going to be the case. I only can see Q is positive and W is negative, but that alone won't be able to allow me to see whether the internal energy is increasing or decreasing, whether it's positive or negative. So yeah, my mistake just now. You cannot actually explain the internal energy increase from thermodynamic first law. You get stuck eventually. So that's the reason why in your current case, your marking scheme use this definition, use this explanation instead. Okay, right? So hopefully this one is clear. Okay, then after that, you move on to the last one. Last question. This one is where you are asked to determine the specific latent heat or vaporization of water. So this one is where you need to use the two different equations. Take equation 1 minus equation 2 or the other way around. All right. So this one is a boiling case. Because this one is boiling case, you know your equation is heat supplied by heater equals to heat to vaporize plus heat lost to surroundings. Okay, so this one is pretty straightforward. Heat supplied by heater is equals to heat gain, is equals to heat to vaporize liquid plus heat gain from surroundings. Okay, so this is the general form of the equation, which would be Q equals to ml plus h which would then be VIT equals to ML plus H. Okay. You do not have power given here, but you have the voltage and current. So I use VIT, not PT here. Okay. You are not given the power rating. Instead, you're given the voltage and current. So I use VIT for Q, not PT, unlike the previous examples. Okay. So this is power rating 1. This is power rating 2. And this thing here is the mass collected over 300 seconds. Okay. So very important. Same time interval. So eventually you get this, where we tell you that Q1 is M1 L plus H, V1 I1 T equals to M1 L plus H. Then Q2 is M2 L plus H, V2 I2 T equals to M2 L plus H. So take equation 2 minus equation 1. You're going to get V2 I2 minus V1 I1 times T equals to M2 minus M1 times L. So just sub in all the values that you have. Eventually you get your answer. So sub in the VIs, sub in the time, and then sub in your masses. Your masses here are in grams, right? This one you have to make sure you change to kg, because it's CA. Actually, you don't need to. Okay, wait, this one. Okay, this one is something I think I better just explain to you. You actually don't need to change your units to grams. Sorry, you actually don't need to change your units to kg. Okay. Over here, you notice that I changed it to kg already, right? So eventually my L is 2.27 times 10 power 6 joules per kg, which again, then I change it to grams. It's kind of like going round. First I change to kg, then I change it to gram. So actually you don't need to do that because of this. Wait, let me just show you why. You could have just rewritten it as just this. Wait, let me just write it down properly for you. 14.2 times 6.4 minus 11.5 times 5.2 times 300 equals to 9.1. What was the value? Equals to 9.1 minus 5.0 times L. Okay. So actually this one you don't really need to change the units because this one is joules per second. This one is second. And then this one is gram. So you are gonna get the answer. Oh, sorry. This is joules per second. Yeah, joules per second times second. If you do the unit analysis, second power -1 multiplied with second power 1, the second will cancel off. So here, you are basically, I think I just write in terms of units for you to see them, you know. Just so it's easier. In terms of the units, you can see that this is joules per second times joules. This one is gram, and then this one is the unit of L. Second, the second here will cancel, so unit of L is actually joules per gram already. Okay, so actually you don't need to do like what I did here. I actually did something unnecessary. You can actually just leave the units in grams because the answer eventually wanted in grams. Okay, right? So this is your answer. 2.27 times 10 power 3 joules per gram. So that one is 1. Okay, now this one is page 19. There's supposed to be 2 more questions. Page 19 we're done. Okay, let's have a look at page 25. Let's have a look at page 25. Okay, I think 25 we can just do it a little. There's actually 3 minutes left. I think we can just do the first page. All right. Okay, just have a look at page 25, November 18, P42. Okay, now define specific latent heat or fusion. So in all your previous examples so far, you were always asked to define specific latent heat only. They never give you a more specific form of the latent heat. They never ask you whether it's fusion or vaporization, but your current question specifically now mentioned fusion. So your definition, you need to be a bit more specific. What phase change is involved? So in your case, you would actually just say this. Heat energy per unit mass to cause phase change between solid and liquid at constant temperature. This is what fusion actually means. Okay, heat energy per unit mass to cause phase change between solid and liquid at constant temperature. This one you need to be specific in terms of your in terms of your in terms of your phase changes. All right, so just be careful of that. Okay, then after that, for part B, you have a student that sets up apparatus shown in figure 3.1 in order to investigate the melting of ice. The heater is switched on when pure ice is melting at a constant rate. The data shown in figure 3.2 is collected, something like this here. Then after that, they tell you the specific latent heat of fusion of ice is 332 grams, 332 joules per gram. State what is observed by the student that shows that ice is melting at a constant rate. Okay, so in your current case here, they want you to explain what should the student observe when ice is melting at a constant rate. Ice is melting at a constant rate here is referring to constant melting. Constant melting rate. Let me just erase it. It's referring to constant melting rate. Okay. So by now, if you know constant melting rate, what does this imply to you? Okay, when you're talking about melting ice right now here. So you should have constant mass of water melted, collected. Constant mass of water per unit time. Per unit time interval. Okay. When you have constant melting rate, it implies to you you should have constant mass of water melted per unit time interval. All right. So this is basically something that you should observe when your ice is melting at a constant rate. So there are a number of things that you can write. The marking scheme actually gave you a few different answers. All right. Now, if you try to write this answer where you say constant mass of water melted per unit time interval, it may not necessarily be accepted. Wait, only the increase of mass in water. Yeah, sorry, it's actually accepted. Sorry, it's actually accepted. It can be accepted. Okay, you can just say it's constant mass of water melted per unit time, or if you want to word it another way, you can actually word it in any of these ways. Okay, the marking scheme gave you a number of answers. Number one, you can say that volume of water in the beaker is increasing at a constant rate. Okay, or rate of increase in mass of water in the beaker is constant. Or level of water rises at a constant rate. And then the less common one will be constant time between drops, constant rate of dripping. These two, I think nobody would really write. This one is actually pretty rare. These first three would be something that most people would be able to write. because you have constant mass of water melted per unit time interval, that you can have this. Okay, your volume of water increases at a constant rate. Your rate of increase of mass in the of water in the beaker is constant. Your level of water rises at a constant rate. Okay, so you can use it to explain this. All right. All right. So then after that, you should have another different question at the end here. Okay, now this one, I think you can just do it as your homework. All right. This one I'll go through with you in the next lesson.